Have you ever caught a fast-moving cricket ball and felt that sting on your hands? That sting is nothing but force in action, and Newton's second law helps us understand exactly why. We already know that when you apply force to a body, it speeds up or slows down. But what's actually changing here? It's the body's momentum, a quantity that combines both mass and velocity. So, when velocity changes due to acceleration, momentum changes too. And Newton realized something profound: force is directly proportional to the rate of change of momentum. That is, the faster the momentum changes, the greater the force. And if mass remains constant, this reduces to the familiar form: force equals mass multiplied by acceleration. But momentum is the deeper idea here. Let's go further. Newton's second law is more than just mass into acceleration. Its most general form is force equals change in momentum divided by time. That's right, if a body's mass or velocity is changing, its momentum is changing. And force is simply the rate at which this momentum changes. In situations where the mass does not change, like most everyday scenarios, this reduces to the simple form: force equals mass into acceleration. However, if the object's mass changes, like a rocket burning fuel, we must use the full momentum-based version of Newton's law. This is why momentum is such a versatile quantity. It allows us to apply Newton's law even in complex or high-speed situations. Now here's a fun insight. Did you know Newton's first law is actually hidden inside the second law? Let's say no force is acting on a body. That means force is zero. According to the second law, if force is zero, then the rate of change of momentum must also be zero, which means the momentum stays constant. And since momentum is mass into velocity, and mass is constant, velocity doesn't change. So the object either stays at rest or moves with uniform velocity. That's Newton's first law, the law of inertia. So in truth, it's just a special case of the second law when no external force acts. What does a change in momentum really tell us? Pause. It tells us that a net external force acted over some interval of time. That is why athletes follow through. Spreading the change in momentum over a longer time reduces the. Let's now derive the equation using momentum. Momentum is defined as mass into velocity. So, change in momentum equals mass into change in velocity, assuming mass remains constant. Now divide both sides by time, and you get force equals mass multiplied by acceleration. Said step by step, force equals open bracket mass into change in velocity, close bracket divided by time, which becomes force equals mass multiplied by open bracket change in velocity divided by time, close bracket. And since change in velocity divided by time is acceleration, we get force equals mass into acceleration. That's how the momentum definition gives us the standard form of Newton's second law, E peak force. Think of a cricket ball that hits the bat and bounces back. The momentum changes a lot in a very short time, so the force is large. This is the essence of Newton's second law in its most powerful form. Force equals change in momentum divided by change in time. Let's apply this to something familiar: catching a ball. When a cricketer catches a fast-moving ball, the ball has momentum, mass into velocity. If he stops the ball quickly, the time interval is small, so the force on his hands is large. That's what causes the sting. But if the cricketer moves his hands backward while catching, he increases the time of impact. And here's the physics. The momentum change is the same, but the time has increased, so the force becomes smaller. Because force equals change in momentum divided by time. This technique protects the player's hands, and it's a perfect example of Newton's second law in action. Now let's look at two more brilliant applications from daily life. First, athletes often land on soft sand or foam rather than a hard surface. Why? Because when they land on sand, it increases the time taken to come to rest. And since force is equal to change in momentum over time, increasing time means reducing force. Less force, less injury. Second, why do glass vessels break when they fall on a hard floor, but not when they fall on a carpet? Again, time is the key. On a hard floor, the vessel stops almost instantly, in very little time, so the force is huge and it breaks. On a carpet, it takes longer to stop, so the force is smaller and the glass survives. These examples show how nature and engineering both use this law to manage safety and impact. So let's sum up everything we've learned. Newton's second law, in its most powerful form, says, force is equal to the rate of change of momentum. When mass remains constant, this becomes the well-known formula. Force equals mass multiplied by acceleration. From cricketers to gymnasts, from rockets to car airbags, this law explains how momentum changes and why controlling time helps reduce force. And remember, even Newton's first law is just a special case of this one. I hope this session gave you a deeper appreciation of how motion, force, and momentum are beautifully connected. See you in the next video, where we continue exploring the forces that shape the physical world.